Hello, everyone, and welcome to our today's episode. Still in discussion of quantitative techniques issues. Today, our study will be based on queuing theory. So, queuing theory is the mathematical study of waiting lines, or what we basically term as a queue. The theory enables mathematical analysis of several related processes including arriving at the back of the queue, waiting in the queue, being served by the server in the front of the queue. And basically, this is a theory that will facilitate permits of the derivation and calculation of several performances as far as the service industry and waiting of lines is concerned. So basically, we shall be in a position to determine how to calculate the average waiting time in the queue, rather in the system, the expected number of clients waiting or receiving a service, and the probability of encountering the system in certain states, such as empty, full, having an available server, or having to wait a certain period of time in order to be served. Before we go to the calculative bit, it is important we understand some characteristics of a single server system, which we shall be basically looking deeper into. One of the characteristics is that the arrival pattern of customers follows a Poisson distribution. And when we talk about a Poisson distribution, it is basically a function that gives a variable elaborating the probability of a particular event to occur over a specified period of time. In other words, we can simply say Poisson probability, it is a count distribution. Either way, it's also important we understand that the service pattern as the exponential distribution. Again, when we talk about the exponential distribution, we elaborate a situation whereby we have a common used measure of the expected time of an event to occur. Further, another characteristic is that there shall be key service station providing a similar service. In our case, we are learning single server, so we only have a single server in the system. Customers, when they come, will be following a single queue. Service delivery is on the basis of first come, first served. Either way, the queue length is infinite and input population is also infinite. And then finally, we say that the arrival rate of the queue is smaller than the service ratio for all individuals in the facility. Now, in this analysis, ladies and gentlemen, I want us to always focus on two main items. One, the arrival of these customers. We are saying they are following a Poisson distribution, and its mean will be denoted by lambda. So this lambda will be elaborating the number of arrivals in 1 hour. That is the number of clients arriving at the service facility in every 1 hour. What is the mean rate of these people? That a particular aspect, we're going to term it as lambda. Number 2, very key item is the service rate. Now, this service rate, we are saying that it follows an exponential probability, and its mean will be denoted by an item. Mathematically, we shall term it as mu. So this mu will determine the number of clients being served in 1 hour. That is, this surface facility, how many number of customers are being served in that a particular hour. Two key things: number of people arriving in 1 hour, and number of people being served in 1 hour. So with these two values of lambda and mean, ladies and gentlemen, you can determine every other aspect we had identified in our introduction. That is, you're able to determine the counter utilization level, which may also be described as traffic intensity, which will be given by lambda divided by mu. You can also determine the probability that there are a given number of customers in the system. And this is given by lambda divided by mu raised to power n, that is the expected number of customers, multiplied by 1 less lambda over mu. You're also able to determine the probability of the system being busy, that you have a client continuous in the service, whereby you use the formula lambda over mu. Again, you can also determine the probability that the servicing facility is idle, which will be determined by having 1 minus lambda over mu. You're also in a position to determine the average number of customers in the system, which is given by lambda divided by mu less lambda. Either way, you can determine the average number of customers waiting in the queue, given by lambda squared divided by, in brackets, mu, smaller bracket, mu minus lambda, close the brackets. Either way, you are also in a position to determine the time in which a client is going to wait in the system. And then you can also determine the time that the particular client may wait in the queue that is before being served. All formula given, if you look at them keenly, you realize that they are using lambda and mu. That is why I was saying the lambda is very key. The number of people arriving in 1 hour. Then mu is also very key. Number of people being served in 1 hour. If you get those two, then the formulas will be given. You can get every other aspect pertaining that a particular service facility. Let's see by an example. I want us to have this a particular example where you have been given that arrival of customers at a service facility is random with a Poisson distribution. 15 customers arrive after every hour, and the cashier serves a customer in 3 minutes. Therefore, you're called upon to determine when the probability that the cashier is idle, the average number of customers in the queue, the average number of customers in the facility, and finally, how long a customer takes in the facility. So in every query that is involving the service rate and the arrival rate, the only two items that I want you to majorly determine how you're going to arrive at them are only two, ladies and gentlemen. One, the lambda, which is called the arrival rate. Secondly, mu, which we termed as the service rate. All formulas will be based on these two a particular item. Some of the queries will give the values directly, so you simply put it down and work with it in the formulas. Some other problems, depending on the narration, they will elaborate a scenario and it's up for you to understand. Depending on how the units have been used, how do you arrive at the correct mu and lambda? Like, for example, in our case, we have been told that the service rate, we have 15 customers arriving in 1 hour. So no calculation. The lambda is 15. In the second important part, we have been told that one customer will consume 3 minutes, meaning that mu is not direct. In this case, we are going to know that if one customer uses 3 minutes, and service rate means how many number of customers to be served in 1 hour, and 1 hour are 60 minutes. Therefore, to get my service rate, I'm gonna take 60 divided by 3. Therefore, I will arrive at my mu as 20. Now we have lambda as 15 and mu as 20. We comfortably move to the formulas, fix what is required, and identify mathematically what units will be required in the different aspects. So now the whole issue is all about using the formulas of the required aspects and fixing the values of lambda as 15 and mu as 20. The first point lets us to determine the probability that the cashier is idle. That will be given by the formula of 1 divided by lambda over mu. That means this will be required by 1 divided by 15 divided by 20. Mathematically, this gives us 1 less 0.75, and therefore the probability of being idle will be 0.25. Just to mention, understand the language here. Sometimes linguistically, you may find the examiner or the author wants you to determine the probability when you arrive, you will be served immediately. That means the system was idle. They may also use the narration that a customer is served when seated and people queue when standing. And they inquire, what is the probability that when you arrive, you will sit immediately? Meaning again, the system was idle. So again, it is important we understand linguistically how the system is being set so as to get the full concept required by the author. Secondly, the system either wanted us to determine the average number of customers in the queue. Formula tells us this we have to get by lambda squared divided by mu, in brackets mu less lambda. Already have lambda as 15 and mu as 20. Therefore, after mixing them, fixing them in the formula, we shall have 225 divided by 20, which has been multiplied by 5, giving us 225 divided by 100. That gives us 2.25. And because we're talking about people, let's round it off and make it 2. persons in the queue. We also wish to determine average number of customers in the facility. Just to mention, facility means the persons in the queue plus the persons being served. And because we are learning a single server system, so always it is only one person who will be at the service desk. Therefore, the service part has only one person. So that means even before we use our formula, by use of common sense, we can identify that the number of customers in the facility will be given by the people in the queue plus one, who is the person being served. For that reason, before we apply our formula, we know that because we have two people in the queue, add one person being served, the people in the system or facility will be three. And true to our words and formula, when we apply the formula of lambda divided by mu minus lambda will give us 15 divided by 3. Therefore, the number of customers in this facility will be 3. Again, we have been tasked with determining how long a customer takes in the queue. The formula tells us to have lambda divided by mu in brackets mu less lambda. Upon fixing lambda as 15 and mu as 20 in the specific parts of the formula, mathematically analyzing it, we will realize that the time in the queue will be 0.15 hours. Then we multiply 0.15 times 60 because our narration is using hours, and therefore multiplying by 60 changes our unit of study to minutes. Therefore, we'll realize that in the queue a customer takes 9 minutes. Again, we have been tasked with determining how long a customer is in the facility. Before we even apply the formula again, common sense comes in and tells us that facility will mean time in the queue and time being served. We have identified from the formula that time in the queue is 9 minutes. At the introduction bit, the author told us that the client to be served, it takes 3 minutes. Therefore, time in the facility, which will include queue plus the service, is 9 plus 3, giving us 12. And it's true in our word. If we apply our formula of 1 divided by mu less lambda, we will realize it will be indeed 12 minutes. The last aspect I want us members to try to see how you've got the concept at personal level. So using the given 3 scenarios, I want you to be able to determine all the aspects of the service facility, like for example, the probability of being idle, the probability of being busy, the length of the queue, the length of the system, time to wait in the queue, and time to wait in the system. The formulas have been given by a previous slide. Either way, you have to come up with your own way on identifying the service rate, that is lambda, and the arrival rate, that is the number of customers arriving in 1 hour. Then either way, determine the number of people being served in 1 hour as mu. Fix those two according to the formula, then evaluate mathematically. If you get your values and you wish to determine if they are correct, try to use that particular email given below, pattersonmoya777@gmail.com. Send your answers and the question. I will let you know if you got the concepts well. Meanwhile, remember to like and subscribe in my YouTube channel as we continue dissecting quantitative techniques. For Shizo.